please subscribe and to like the video, leave a comment. All these things help the YouTube algorithm show the program to more and more people. And we're here to help spread the word about climate action and the dangers of climate change and what we can do about it. That's a pretty important message, probably more important than a lot of other things on YouTube. Yet, without your help, we can't really get the message out. So we really appreciate that if you could help us. And it's free. So like and subscribe. So our first misconception, and perhaps in some sense the most important one, because I think this is something that the general public believes, and that is, sure, climate change is a problem. Sure, we put CO2 into the atmosphere, and that's a bad thing. Yeah, it's getting warmer. And by the way, I'm here in New York right now, where it's been really warm the last few days, and people are aware that there's something different, something's going on. But they also feel that, look, once it gets really bad, we will cut our emissions and we'll get them down to zero if we have to, and then things will be better. Well, that's the misconception. And the reason that's a misconception is that I believe that most people have a model in their head of pollution. For example, water pollution or air pollution. With like water pollution, you live on a river, you go swimming, you go fishing, you like it and everything, but then someone builds a chemical plant upstream of you, they start releasing toxins, and you can't swim or fish anymore. But you get your buddies together, you get political pressure, and you either shut down the plant or you get them to clean up their emissions into the water. And then a year or so later, you can go swimming and fishing again. That's the model we have in our head. And it works for lots and lots of things, lots of different kinds of pollution. But it doesn't work for CO2. Because CO2, while some of it's immediately absorbed by the ocean lands and plants when we put it up there, the remainder stays in the atmosphere for hundreds to thousands of years. And in some small amount actually remains in the atmosphere for 500,000 years. So when you finally stop emitting, things don't get better. But if you're lucky, they stop getting worse. And that's only if we're really lucky, because we're going to talk about what else could happen in other sections here. But this is the most important, I think, thing for the general public. They're not as worried about climate change because they think when we finally get around to fixing it, we'll just fix it and we'll just stop emitting and then things will get better, just like the river would get better. Or if you have dirty air and you stop the coal plants, then the air clears up. That's true for those kinds of pollution because in the water, it lasts for just days before it's washed downstream. In the air, that kind of pollution lasts for a week or two, and then it falls out. So if you stop those things, they get better. But things that last in the atmosphere for hundreds to thousands of years don't get better. So really, a really important one. But let's move on to others. Another one I've been seeing actually recently, like on Twitter and Blue Sky, people talking about, they realize that if you just focus on our emissions reduction, we're going to get up to 3 degrees Celsius. And they realize that's not good, but they kind of see it as being twice as bad as 1.5. And we're at 1.5 now. And while things are hot and while some things are happening that are unusual, like, seeing lots of cars floating down the middle of the street and having, rain amounts never before seen, or having heat waves in Europe never before seen, and these kinds of things. But we're still here. We're still surviving. We're still a civil society for the most part. Well, that you might question that at times, but anyway, so that's the idea. But that's also not true. It's a little bit more like having a fever. If you have couple of degrees of fever, you'll kind of feel bad. You'll take some medicine, you'll take some Tylenol and put a wet washcloth on your forehead, and and then you wait a few days and you get better. Now, if you had like a 4 or 5 degree fever, you would probably go to the hospital, and then they would treat you much more seriously, because this is now a life-threatening type of fever. And if you actually have a few more degrees than that, you die. And I think it's better to think of the world's climate similar to having a fever. A small amount of fever is bad, makes you feel bad, or in case of climate, you get some unusual heat waves, you get intense rains, you get all of these things that put a stress on your infrastructure and on society, but probably doesn't break it. But you now go from 1.5 C to 3 C, and it's not linear anymore. At 3 C, let's talk about what happens at 3 C versus 1.5. So one thing is that we'll pass many tipping points. The tipping points, we believe they begin around 1 to 1.5 C for the easiest to trip ones. And then the other ones come after that around 2. And by the time you're up to 3 C, you've passed many of these tipping points, including AMOC collapse, which we're on track to tip even with 1.5. Greenland and Antarctic ice sheet collapse, which again are happening anyway, at least in certain parts, but this would accelerate them greatly. And I also want to point out with Greenland, once you melt the top of Greenland, which is very high, ice that's very, very high, it goes a little bit lower and temperatures get warmer as you go down. So you get a self-fulfilling thing where once you melt it far enough, it really can't build back up because it gets warmer as the peaks lower. And together, those things can add hundreds of feet of sea level, although in the near term, it will probably only be 10 or 20 feet, but that's still an incredible amount of water to inundate all our coastal cities, as just one example. Now, the other thing that happens is as you increase the average temperature a little bit, the extremes go up a lot. And that also applies to rainfall, because as you increase temperature, that increases the average amount of water vapor in the atmosphere. A 1 degree warming gives you about 7% more water vapor. We're at 1.5, so we have about 10% more water vapor on average. But when you increase the averages a little bit, the extremes go up a lot. We can do a whole show on that, but we won't do it now. But just today, we're seeing weather events that we would consider to be 1 in 1,000 or 1 in 1,000 years. We might see something like that, and now we're seeing them like every 5 years or every 3 years. So that's happening today at 1.5. But once you get into the 3 degree territory, now you're going to see what we're formerly, we say 1 in 1,000 is a 3 sigma, 3 standard deviation event. But now you're going to get to 4 and 5 standard deviations. So you're going to get into like the 1 in a million event category would be happening every few years. And this would be just mind-boggling amounts of rain, for example, unsurvivable heat waves, and things like that would really impact both humans and our infrastructure, as well as wildlife and plants around the world. So these things are far, far worse than even though what we see at 1.5 is pretty bad, they'd be far, far worse at 3 degrees. As I just mentioned, you could have heat waves where large amounts of the earth are uninhabitable. You can't survive outdoors because you can't sweat enough to cool fast enough, and you actually just die. That we're sort of reaching those temperatures today for old people and babies and people that maybe not in the top health, but this would be for sort of everyone if we keep warming. We're already in a mass extinction event. 3C warming would accelerate that. In fact, 3C is halfway to the biggest mass extinction event in history. 252 million years ago, Earth warmed about 6 degrees of Celsius, and essentially 90% of life on Earth perished. And we're heading to another mass extinction event. But the other mass extinction events began over thousands and thousands of years of very slowly increased CO2 due to, for example, volcanoes that kept emitting and things like that. Very, very, very slowly increasing CO2 in the atmosphere. But we're doing it over 100 years. So it's a very, very different situation. And there's much, much less time for species to adapt to the changing conditions. As our friend Kevin Anderson said on this program, originally this was for 4C, that it's not compatible with an organized global community, which means sort of, think of civil society collapsing. when he was on the show last time, he said, well, actually, it might be closer to 3C because we're seeing that the impacts of warming are more than we thought they would be. And so what we thought 4C would be is probably 3C. And one thing about getting to higher temperatures is it triggers climate feedbacks. For example, melting permafrost, release of clathrates, which are frozen methane under the oceans, and things like that, that would cause the Earth itself to give off more greenhouse gases. So it would sort of be out of our control, where we can shut off our power plants, our gas-fired power plants, and stop burning coal. But once the Earth starts releasing methane and CO2 from permafrost and clathrates and things like that, then we don't control it anymore, and that would lead to higher temperatures. So even though we would hit 3 degrees, it could lead to 4, which could lead to 5. And we don't want to get in that situation. So that's 1.5 versus 3C. So that's number 2. Let's move on. And again, these are not in a particular order, and they are kind of jumping around, as you'll see. But it all sort of all together makes sense, I think. Let's talk about the recent heat wave in Europe. There was a bunch of people, including what they call lukewarmers, which are not people that deny climate change, but they deny that climate change is a big deal and we should continue burning fossil fuels because fossil fuels are so good for society. They provide so much value that even though, climate change is real and everything, let's not worry about it too much. And then, of course, when they're presented with a heat wave that's killing tens of thousands of people in Europe, they say, well, that's because Europe has policies to prevent people from buying air conditioners, which itself, I mean, there are rules and regulations around historic buildings that you can't put an air conditioner on the outside of a building that's designated a historic landmark or something. But of course, there's all kinds of air conditioners, including indoor air conditioners and things like that you could use. So then, but the point is that, if only Europe had air conditioning, then these heat waves wouldn't be a big deal. So, one thing you might have seen, there was the top weather person, meteorologist in France in 2014 gave a mock weather forecast for 2050, where she showed these very high temperatures. And it turns out that the temperatures from the past week in 2026 were actually higher than her pretend forecast for 2050. And so that's part of all of this, I guess. But the bottom line is air conditioning actually would help people in Europe be able to survive the heat wave better than without it. That seems to be clear. And in places like in the southern United States, where it gets very hot and humid for big parts of the year, one reason that it's populated down there is because of air conditioning. But however, air conditioning does nothing for people who work outside. And of course, it does nothing for the plants and animals that live outside, as well as for agriculture, which is impacted by the heat. And in fact, Europe's about to have a third major heat wave in a row, and it's really going to devastate agriculture. And that raises the price of food and causes all other kinds of problems, of course. The other side of it is that while you might feel cool inside, there's infrastructure outside that is just not meant to handle these kinds. Europe was not built for these kinds of temperatures. One example was a streetcar in Austria, maybe, and sort of the glue or the tar that was holding the rails in just melted and was flowing out of the tracks into these big clumps. And if it was in Phoenix, they would have used a different kind of material that doesn't melt that easily, but then it might have trouble in the cold. So bottom line is that things are not designed for this. And in fact, when we get these huge rainstorms, our infrastructure is not designed. And it's almost impossible to design for rainstorms that are 10 inches in a day. I mean, 3 inches in a day is a huge amount of rain. 10 inches, 20 inches. I saw 30 inches in Italy a few years ago in 24 hours, which it's impossible to build infrastructure to handle that. And I should also point out that air conditioning is a climate feedback. As the world gets warmer, more and more people use air conditioning, and that uses more energy. And currently, space cooling, or cooling rooms using air conditioning, uses 5 times more energy than data centers use. And everybody's up in arms about data centers. So I'm not saying we shouldn't use air conditioning, but we should recognize that it is a climate feedback. And as we'll talk about later, even if you made an efficient air conditioner, that would actually increase energy use even more. And I would just argue that this is somewhat in jest, but people claim that things that make the world better or easier to survive in the climate world, for example, we'll talk about solar radiation management later on, they call that a moral hazard because it gives you, if you feel better, then you won't have as much incentive to lower emissions. And they say, of course, we have to lower emissions. That's the number one thing we need to do. And so, but however, I would just argue, but air conditioning makes you feel better too, and takes your mind off of the crazy heat wave outside. And that could be a moral hazard as well. I'm just sort of making the point that the moral hazard argument is a rather weak argument, and we'll get back to that a little bit later as well. Okay, so let's keep going. This one is a really big one among, I call them climate action people. Again, everything I'm talking about here is not climate deniers, but people engaged in climate action, climate scientists, climate advocates. And just like with many causes, everyone has their own point of view of what the most important thing is. And one of the things that seems to be fairly consistent is that there's a big group of people, again, people dedicated to climate action, who say the number one thing we must do is reduce our emissions. Everything takes a back seat to that. And when we talk about doing carbon dioxide removal or CDR, don't do that because emissions reduction is many times more efficient than that. And that actually is true. It is true that it costs far less to reduce emissions than it does to remove an emission using carbon dioxide removal. In other words, rather than just shutting off a coal plant, hey, I'm going to let that coal plant burn its coal, and then I'm going to use CDR to capture that CO2 that the coal plant made. That's a stupid thing to do. And I agree that's a stupid thing to do. But that assumes that we're using CDR. And let me say, by the way, there's carbon dioxide removal, which is sort of the word to mean all kinds of carbon capture. There's CCS, carbon capture and sequestration, meant for a point source, such as a cement plant, to capture from that, put it underground. And then there's things like DAC, direct air capture, where we capture CO2 out of the atmosphere. These are all different kinds of carbon capture. I'm kind of lumping them all together here. They have different costs and different amounts and things like that. But they're all meant to, well, CCS is actually meant to lower emissions. It's a way, if you don't know how else to, if you still want cement, but you don't want all the emissions of cement, you can strap a CCS system. We're going to talk about CCS later as well as one of the misconceptions. But for now, we're just talking about emissions reduction versus doing CDR. So in some sense, since it is so much cheaper, if you had a limited budget and you only had, let's say, $10 billion, and that's all the money you could spend, or $10 trillion, pick your number, you do the math and say, you know, I should spend all that money on doing emissions reduction, because that's going to give me more lowered emissions than if I spent any of that money on CDR, since CDR is so much more expensive. That's true. But there's a number of things happening. First of all, we're not lowering our emissions. Fossil fuel emissions are at a record high. And I guess you could argue that if we hadn't done all the stuff with renewables, that fossil fuel emissions would be even higher than they are. But it doesn't really matter, because they have to come down dramatically right now, and they're still going up. So there's a disconnect there, and this argument that we have, that we have to spend all our money on lowering emissions is not correct, because we're not doing it. Also, the emissions that we do now, as we just talked about, they stay in the atmosphere for hundreds of thousands of years. So we have to remove those too, because CO2 emissions in the atmosphere are already too high. It's 50% higher CO2 in the atmosphere than pre-industrial times. So the purpose of CDR is to remove the past emissions. We've emitted 2.7 trillion tons so far. We do about 50 billion tons a year, less than that just fossil fuels, but with land use changes and everything, it's about 50. And if we only do emissions reduction, again, we say, hey, well, that's the most cost effective. If we only do that, then we will go over 2 degrees and we will go over 3 degrees, and that will be utterly catastrophic. So the plan to, quote, optimize money spending of some kind ends in catastrophe. So therefore, I think that's not a good plan. And I haven't seen this proof anywhere that there is a fixed budget for saving civilization. Like there's only a limited amount of money we can spend on carbon dioxide removal, on reducing emissions. There's a fixed budget. Of course, I still see we're building cruise ships and we're building golf carts and we're building all kinds of stuff not related to climate. And we have money for that. So there seems to be a lot of money around. It's just that we're not using it on the things that are going to save our ass. So I would argue that we should not only do emissions reduction, but we should also spend money on scaling up CDR so that we have it available as when we need it, which is actually right now. But in the next 10 or 20 years, we're going to need it at scale. And if we are just starting it, then it's going to take a long time to scale it up. So that's some of the reasons. And again, it's actually there are inexpensive ways to lower emissions. The simplest way is to phase out fossil fuels using policy. It almost costs the government nothing. In fact, it will save trillions of dollars because it turns out that renewable energy is cheaper than fossil fuels. And we're spending a lot of money on subsidizing fossil fuels. And the price of fossil fuels does not include the 8 million people a year that the fossil fuel pollution kills. It doesn't include the cost of adapting and rebuilding from climate events. All these things are very, very expensive. It's not included in the cost, but it's real. So if we want to save money, we simply phase out fossil fuels. Renewables will scale up to replace that, and then we'll have money left over for doing CDR. So it kind of all works if we think about it the right way. So let's keep moving on. So there's also a lot of what you see if you're looking at Twitter or Blue Sky, you see a lot of charts showing that solar, or sometimes renewables altogether, are finally beating out coal. Here's a classic example of that. Here's a chart showing renewable energy use in the green. And this other line, I got to go over here. This is the coal line up here, which is still going up, but you can see that the renewable line is about to cross the coal line. And that's great. That's really good. But the problem with this chart is this is not energy use. This is electricity production. Electricity production. Electricity production is about 22% of global energy use. So you're taking a small segment of total energy use, the thing that renewables actually does well, which is produce electricity. And you're saying, hey, we've solved the problem. But let's take a look at what total energy, and this is what's called final energy. So it doesn't even take into account that we have to burn a lot more fossil fuels to get the energy we need, because fossil fuels are very inefficient at producing electricity. But this is just talking about the actual amount of useful energy they produce. So it makes fossil fuels look better than they really are. And yet, even with that, the bottom three here, the dark gray, blue, and light gray fossil fuels, they're just growing. And the renewables, which are up here, yeah, they're growing too. And if you only looked at electricity, they would look pretty impressive. But when you look at them in a total energy point of view, which is what the world cares, that's what climate cares about. It doesn't care about how much electricity versus cement you make versus other things, cares about, or heating that you do. It cares about your emissions, and that's based on the global total output. So that's one example of a kind of chart that's deceptive. Now let's move to another one. You see a lot of these charts where the y-axis is 0 to 100%. So this is showing the mix of energy, and this is from 1776 until 2025. And this green area is wood, because before we had coal and oil and natural gas, we used wood for heating our homes and for most kinds of energy, right? And for cooking and things like that. And if you saw this chart, you would think that the amount of wood used for energy has dropped dramatically from the 1700s to, let's say, 1950. Excuse me. Excuse me for a second. But that would be actually incorrect. Let's take a look at this graph, sort of the same graph, but not as a percentage graph, just as an absolute energy graph. Whoops, sorry, here we go. And here, this green line is the wood, which was very small back then, even though it was 100%. And it's kind of stayed the same all the way throughout here. Then they combined it with other renewables here, so it started going up. But as you can see, even though it looked like it dropped dramatically, it didn't. And the problem with this is the same is true for fossil energy. When you show solar as a percentage, it looks like it's eating into the amount of coal or natural gas being used. But as you can see here, even though looks like coal dropped here, by the way, and that's because this is a US energy supply, not a global energy supply. As a global energy supply, coal is continuing to go up. And one reason that coal dropped in the US is that we switched it with natural gas because it was cheaper to use natural gas for electricity than coal. And so we just swapped them out. And that sounded like a good idea because it theoretically lowers emissions, because natural gas has half the CO2 emissions per kilowatt hour that coal does. So you think that would lower emissions. But in reality, natural gas is really made of methane, and there's something called fugitive emissions or leaks of the methane that get directly into the atmosphere. Methane is 120 times more powerful than CO2 at warming the earth while it's in the atmosphere. So this switch, while it's counted as lowering emissions, actually increases global temperatures when we switch from coal to natural gas. Also because coal gives off pollution that reflects the sun, and natural gas doesn't really do that. So that because of those reasons, this switch in the US, which made it look like emissions are going down, actually made the global temperature go up. So that's a whole separate thing. But anyway, so that's these charts are very often they're often deceiving. Basically anything with a percent on the y-axis, just ignore that graph altogether. And when you're looking at these other graphs, make sure you're looking at total energy, and you're making sure you're looking at global energy, and then you should be okay. So what's going on here? I think we talked about this. Electricity production is only 22% of final energy consumptions. Percents don't matter. Only absolute emissions matter. And by the way, it really is irrelevant how much renewable energy you use on Earth. You could have 10 times more renewable energy tomorrow, and if you had the same amount of fossil fuel energy, nothing would have improved. In fact, probably things would get worse because the mining and extraction and manufacturing to make all that renewable energy. But even if that was carbon free, it wouldn't make any difference, because renewables don't cause climate change and they don't stop climate change. They're neutral. That's why we like them. But the thing we have to focus on are the absolute amount of fossil fuel emissions. And also, just as I mentioned, U.S. numbers are interesting, but it's global numbers that matter. Okay. Another thing I see all the time, especially in climate investing, like climate solution investing, you see a lot of companies that are focused on energy efficiency. And if you can use less energy per unit of work, like if you can cut the well, we're going to talk about a specific case. Let's talk about the Watt steam engine. The Watt steam engine was an amazing thing. James Watt invented it, and it was a steam engine that literally used 75% less energy for a given amount of work output compared to the earlier steam engines of the time. And it's really interesting how this worked, and it's an interesting story, but it's true. It really was that much of a breakthrough in terms of lowering energy. And it's interesting how he did it, but that's for a whole other show maybe. But the point is, in England, where the Industrial Revolution was happening, they said, hey, this new steam engine uses so much less coal, per engine, that our coal supplies are probably going to last a lot longer than we thought they would. And they hired this guy, William Stanley Jevons, William Stanley Jevons, to study this. And he looked into it and realized that no. The more efficiently you use a resource, the more that resource is used. And if you use some slightly different wording, it all makes sense. When you say I've improved the efficiency of this thing, say instead I've lowered the cost of this thing. So in this case, he lowered the cost of energy by 75%. So when you lower the cost of something, what happens? You sell a lot more of it. And if you lower the cost by 75%, you don't just sell 4 times more. You don't even sell 10 times more. You sell 100 times more, or more, even more than that, especially when it comes to energy and computation, both things that we have an insatiable appetite for at the right price. So what happened, of course, was this really kicked off the Industrial Revolution. The reason we have climate change today like we do is because James Watt invented a steam engine that greatly improved energy efficiency. We know this, it's very clear. I mean, and Jevons wrote a book about this in 1865, and no one's contradicted this book since. I mean, there's no one who says, no, the rebound effect isn't real. But when it comes to their own particular thing they're working on that improves energy efficiency, they don't count the rebound effect. I see this all the time. And instead, they just say, oh, we're cutting the use. Let's say we make a car that's more efficient. Let's look at that as well. But the bottom line, here's the thing to remember, that improving energy efficiency increases energy use. Not always, not in every case, like maybe with refrigerators or some other thing that limits the number of refrigerators out in the world. So maybe you can not have a complete rebound effect on that. But when it comes to energy production or computation, both those things are insatiable, and they all have rebound effects that are more than 100%. In other words, the more you improve their efficiency, the more total energy we'll use. The individual light bulb will use less energy, but we have a lot more light bulbs now than we used to, that kind of thing. But there's another case, and that is during the Obama administration, rather than put a price on carbon or really tackle climate change, they instead increased fossil fuel production and was proud of that as the all of the above energy policy. But they had to do something to show that they really cared about climate change. So their focus was on improving the fuel efficiency of cars. And okay, so what happens when you improve the fuel efficiency of cars? Well, one is you lower the energy use of a particular car going a particular distance. And that's true. But there's sort of a bunch of indirect rebounds. And so one, if you have better fuel economy means lower cost to run the car. And so you're more likely to drive the car farther or with less people in the car with you. Maybe you just drive solo more often because it's so cheap. And of course, because fuel is running a car is cheap, you buy a bigger car. And we had an explosion of SUVs that totally wiped out any of the potential savings of this Obama era policy. And that's just right there. But on top of that, we have lower fuel bills because we don't have to pay as much, again, if we didn't buy the bigger car. And then we have more savings, and then that bank uses that money to build more infrastructure and lends it to fossil fuel companies to drill more wells, so you get more energy use that way. And also, hey, we just saved $1,000 this year. Now let's take that trip to Spain. And so again, when the money is saved because of energy, it goes to something else very often that uses energy. And then, of course, you're also building in the whole idea that everyone has to have a car, that we need roads everywhere, and cities have to be built for roads, and so you don't have walkable cities anymore. All of these things happen when you do simple things like, hey, let's make cars more efficient. In fact, one way to think about it, you can ask the question, what will use more total energy if all cars got 100 miles per gallon or all cars got 1 mile a gallon? Now you say, well, all cars got 1 mile a gallon. That would use so much energy. It must be more. No, it wouldn't be more, because who's going to drive a car where it costs $5 a mile? If let's say, fuel's $5 a gallon, it would cost you $5 a mile to go anywhere, and it would be way too expensive to go anywhere. So you're not going to use it. But 100 miles a gallon, well, that's much cheaper, and then I can afford it. That's 5 cents a mile, and then for the gas, and so these things make a difference. And anyway, that's efficiency. The bottom line is that efficiency is not the way to lower emissions, but it's not always true. So, by the way, this is another graph where the IPCC is trying to show, hey, this is how we lower our emission. This is what the emissions would have been here. And the green is like we switched away to fossil fuels, and the blue is energy efficiency. And so it shows energy going down because of energy efficiency. But of course, energy is going to go up because of energy efficiency, not going to go down. And then they do these other things about fuel swapping and things like that, which are all the same thing as reducing fossil fuels. So they're double and triple counting reduction of fossil fuels. Anyway, so this is like fantasy stuff going on here. But the bottom line is that normally energy efficiency leads to cheaper energy per unit of work, and therefore the amount of usage goes way up, and therefore it increases energy usage. That's most of the time. However, if the efficiency gains are in response to a price on carbon, where you're taxing carbon use, or you have a policy to phase out fossil fuels, so fossil fuels now going to get expensive because you're not allowed to use a lot of them, and then people compete for them. So people will do more energy efficient things in response to that. When the energy efficiency comes in response to the price signal, then you don't have a full rebound effect. But when you just have energy efficiency and just makes everything cheaper, that's when you have the full rebound effect. Okay, let's keep going. We're jumping around here. I know it's keep it all straight. We're number 7. Carbon dioxide removal doesn't work, and it hasn't scaled like was predicted. So first of all, let's just take a look at that. Here's some CCS again, is the point source version of CDR, carbon capture and sequestration. Carbon dioxide removal is CDR, but roughly the same things here. CCS technology has captured just 0.001% of global emissions in the last 50 years. Well, that sounds like, wow, this whole thing doesn't work, does it? And first of all, that number I think is right. That's fine. But we have to realize what's going on here. CDR, carbon dioxide removal, and CCS is a waste disposal technology. It's a way of capturing CO2 pollution, either before it gets into the atmosphere or once it's in the atmosphere, and then doing something with it, either turning it into rock or injecting it deep underground so it can't get out anymore. And that's waste disposal. It's a cost, just like taking your garbage away from your house. You pay the waste disposal company to take your garbage away. Now, if you were allowed to throw your garbage in your neighbor's yard and didn't have to pay anything, that would save you a lot of money, and you might just go do that. But it turns out that's illegal and you get arrested, so you don't do it. But however, when it comes to CO2, you are allowed actually to throw your pollution into everyone's backyard, into the atmosphere, and pollute the atmosphere for free. And you're allowed to do that. And so why are you going to pay, or why is anyone going to pay for CDR? So people confuse the fact that CDR hasn't grown, and they think it's something inherent about the cost of CDR, or CDR technology doesn't work, or anything like that. It is true that CDR is expensive now, and it's going to be expensive for a while because we're running it at 1/10 millionth the scale we need it to run at, we have to scale it up by over a factor of 1,000,000 times before it's removing gigatons of CO2. And that's what we needed to do. We need to remove gigatons, tens of gigatons of CO2. And it is possible to do it, but it's certainly not going to happen on its own. No one's going to pay for it. So until governments either pay for it themselves or pass policies that require people to use it. For example, they could easily pass a policy that says airlines have to capture as much CO2 from the atmosphere as they emit into the atmosphere with their planes. And after this scales up a bit, it currently would probably cost about $500 a ton to do that, but eventually we get to $100 a ton. And at $100 a ton, it would add $1 per gallon to the cost of aviation fuel. Aviation fuel went up more than that recently. And so, this could all be done. And a policy like that would cause CDR to scale and be used. So we shouldn't fool ourselves to think that CDR is some expensive technology that will just blossom on its own without anything else happening. Another corollary to this misconception is that the only thing that CDR is good for is supplying CO2 to the oil and gas industry so that they can use it to pump underground to pull up more oil. And it's enhanced oil recovery, EOR. And it is true that I think the number one commercial use of CO2 is for that. But the reason for that is EOR is like the number one commercial value of CO2. It's soda, putting it in soda, which requires a very clean version of CO2. It's using it in greenhouses, which is a pretty small amount. And then there's EOR, which is a very large amount. So until we have policies that give people another reason to do it, the only way you can get away with doing CDR is by selling your CO2 to the oil and gas industry. Now, some of that does stay underground. You can argue that that's still a good thing, but a lot of people see it as a terrible thing. And I think we should be phasing out fossil fuels, not encouraging them. But we have to do it we still have to remove CO2 from the atmosphere. Otherwise, we essentially don't survive. So it's a good thing to figure out the right policies that would make all that happen. So let's move on. SRM is a crazy idea. Are you out of your mind? Are you going to screw around with the climate? So SRM stands for Sunlight Reflection Methods, also solar radiation management, also known as solar geoengineering. And it basically means that we would artificially, on purpose, cool the Earth. And people think that's a crazy idea. Why do they think it's a crazy idea? Well, three major reasons. There's probably some others as well. First, they're concerned that it will have negative side effects. For example, it might disrupt the monsoons and shift storm patterns and things like that. It might even help one country, but make it worse in another country and these kinds of things. So that's the negative side effect problem. They consider it to be a moral hazard. If you cool the Earth, then people don't have as much incentive to reduce emissions. So that's a bad thing. And we talk about why they think reducing emissions is the number one thing that we should be doing, and our sole focus should be on that. And then another problem is that there's no effective governance institutions in place that can fairly and justly decide how and when to deploy SRM. And all of these, well, the middle one's not true, but it does have negative side effects, and there aren't governance institutions in place. But let's talk about these. So what's really going on? Well, the side effects, it's true that there would be some side effects. The last time SRM was implemented wasn't by us, but it was by the Earth, and that was in 1991 when Mount Pinatubo threw about 20 million tons of sulfur dioxide into the stratosphere. So a very, very large volcano will throw sulfur into the stratosphere. A regular volcano won't reach up that high and doesn't have this effect. But Mount Pinatubo cooled the Earth about 0.5 degrees for 2 years. And so, and yet it did have some negative side effects. It affected growing seasons in certain places and weather patterns and all these kind of things. But we're still here, so we know it wasn't an utter catastrophe. But the problem is to talk about SRM having side effects without talking about the side effects of not doing SRM is a little bit like talking about chemotherapy without mentioning the word cancer anywhere. I mean, the only reason you do chemotherapy is because you have cancer and you will die if you don't take it. And then the fact that you get nauseous and lose your hair and whatever and feel really bad is accepted because you're doing something. Well, SRM doesn't have those kind of bad side effects, but it could have side effects, but nothing close to the fact of the side effects of not doing it. Crossing tipping points, making Earth uninhabitable over vast swaths of the Earth, incredible rainstorms, AMOC collapse, on and on and on. These are the things that if you want to argue against, you want to complain about the side effects of SRM, I believe you're required to talk about the side effects of not doing SRM. And for some reason, people get away with just bringing up one without the other. It's very strange. It's a little bit, of course, it's also the trolley problem. We did a whole show on that, whereas people care far more about causing injury to a few people if they're responsible versus not doing something that causes injury to 100 or 1,000,000 times more people, as long as they can claim I didn't do it. So anyway, that's a whole discussion. We did a whole hour on the trolley problem. Look that one up. So the moral hazard argument, first of all, it's not even true. We don't reduce our emissions because we're concerned about climate change. We reduce our emissions because it's cheaper. And we did that with switching from coal to natural gas, which actually heated up the Earth, but we counted it as emissions reduction. We're now doing wind and solar or deploying at an incredible rate, but that's because it's the cheapest form of energy like ever. And all 90% of all new electricity production are wind and solar. Again, not because of climate reasons, but because it's cheaper. So the whole premise of the thing is wrong. But the other side of it is SRM, we did a whole show on this, actually reduces emissions because warming causes feedbacks that cause warming. So warming causes the Earth to give off greenhouse gases, which causes more warming. And this is part of what the equilibrium climate sensitivity is. Like when a doubling of CO2 causes 4.5 degrees of warming, but only like 1.2 degrees of that is from the CO2 itself warming the Earth. The rest are the feedbacks that cause the Earth to warm. So doing it the opposite, doing SRM and cooling the Earth, causes feedbacks that cool the Earth and reduce emissions on a massive scale, by the way, compared to the stuff we're doing. So if you are concerned with emissions reduction, then you want to do SRM. And it turns out we don't reduce our emissions because of climate change. And therefore, renewables will still be cheaper, even if we cooled the Earth and didn't let the Earth go to pot. And also, I would have to say, too, that the people suffering today the most are people in the global south and developing countries. And the whole idea of keeping the, quote, pressure on people to reduce emissions are wealthy nations. So basically, the wealthy nations, when you make this moral hazard argument, are saying, oh, we should try to push wealthy people. We should keep the world, like the global south people suffering, to give more incentive for the wealthy people to reduce their emissions. I don't think that's a fair and just way to do it. And as with governance, it's true. We don't have a good governance structure in place. I think if a comet was heading our way, we wouldn't have a good governance structure in place, but that wouldn't mean let's not do anything about the comet about to hit us, although that's what happened in the movie Don't Look Up. But if we're intelligent, we'll figure out how to solve that part of it. And if we don't do it, well, then we end up in a world where we don't have any governance of any kind because we get to the point where it's not compatible with an organized global community. All right, 2 more to go. Let's see. We got renewables can't provide base load power. So first of all, what is base load power? Base load power is simply the minimum energy demand. That's all it means. It's that, your energy demand goes up and down during the day, and your base load is the minimum number. And it's not really have anything to do with the energy supply. In fact, quote, base load providers of like a coal power plant, while it used to be a nice thing to have, are now a liability. Well, one reason, it's very expensive, but the other reason is it can't ramp up and down very quickly. And the fact that during the daytime, solar power can beat the pants off the price of coal power any day of the week It means that the energy buyers are going to want to use solar then, and that means that the coal plant needs to shut down or lower its output, and it's hard for them. It's easier for a natural gas power plant to do it, very hard for a coal plant to ramp down its power. So these are sort of inefficient power plants nowadays, where they used to be okay, but now with a mix of energy suppliers, it's a liability, no longer an advantage. Battery prices are dropping dramatically, incredible, actually. They've dropped 90% in the last decade. They'll probably drop another 80 to 90% in the coming decade. And they're just getting so cheap that today batteries are cheaper than gas peaker plants for meeting peak load energy. And within the next 10 years, as wind and solar and battery prices keep dropping, the combination of solar and battery will be cheaper than any kind of fossil fuel energy going forward. So, and then you basically have, quote, what base load, you have flexibility with batteries that you didn't have without them. And so this is really a non-issue. You can also overbuild wind and solar so that when you have a cloudy day, you still have all the energy you need, or if it's not as windy as it normally is, you still have all the energy you need. And then when the sun is shining, and then when the wind is blowing strong, you have vast amounts of extra energy, which you could use for things like desalinization, decarbonization, and things like that. And we also have something called demand response, and we're using this today, and we could scale this up a lot, where a factory agrees to use less power when the power company says, hey, it's a hot day and everyone has their air conditioners on, so we need you to roll back your energy. They get a discount on their energy when they do that, and they can plan around that and maybe run the plant at night or something like that. So all of these things mean that the whole baseload thing is a non-issue. That's the bottom line. And number 10, drum roll, please. Let's just plant trees. What? I mean, that seems so simple. And you see this a lot. People just say, let's just plant trees. Hold on. So let's look into what that means. So how many trees would we have to plant? Well, let's take a number. Let's do 50 gigatons. So 50 gigatons is 1 year of fossil fuel emissions plus, which is like 35, 40 gigatons, plus the land use change, which means like deforestation. And probably if you throw in forest fires and everything, you get over 50 gigatons of emissions. So let's say we wanted to plant enough trees to offset 1 year of human emissions. What would that take? Well, that would take about 2.5 trillion trees, and they would have to grow to maturity over several decades in order to capture all that carbon. So it's not even something that's offsetting this year's emissions. It's going to take 20 years, 30 years to actually do this. Again, we're talking about 1 year of emission. And the Earth currently has about 3 trillion trees. So we're talking about just to offset 1 year of human emissions, we'd have to almost double the number of trees on Earth. And the land area, because you have to space them out and everything, would be about 3 times the area of the United States. Again, for 1 year now. And that would cause, obviously, an ecological crisis of finding non-agriculture available land. And then, of course, the water, twice as many trees on Earth. And that the water's going to come from somewhere. Fresh water. Another problem is you're going to plant a lot of these trees in areas that are currently light colored ground, either sandy ground or with brush that's not very dark. And then you put a dark tree with a dark canopy on it, and that will actually increase solar absorption and therefore increase global temperatures if you don't do it right. So you have that problem. And then, of course, you're doing this in order to store the carbon. You took carbon from underground that was stored away a couple 100 million years ago. You drilled a hole, you pulled it up, you burned it, and put the CO2 in the atmosphere. You now want to store that. Well, if you store it in a tree, the tree will store it for a while, but then that tree will be impacted by fire, flood, drought, heat stress, old age, bark beetle, disease, and all other kinds of things. And that tree will die and give its CO2 and maybe even methane back into the atmosphere. So you don't even have a permanent, you did all this work, you doubled the number of trees on Earth, and you didn't even permanently sequester the carbon. So in order to sequester geologic carbon, which is stuff we got from underground, we should store it using geological methods, like turn it into rock or pump it back deep underground where it can't come out. And as Kevin Anderson said, I mentioned him earlier, plant trees for good tree reasons. Don't plant them for carbon reasons. And this is one of the reasons why. And I just want to emphasize one more time. I was only talking about 1 year of emission. We've emitted 2.7 trillion tons. So obviously there's not even theoretically possible to plant enough trees to make up for that. So with all of that, don't forget to like and subscribe. And also, in the comments, let me know what was your favorite of these top 10 things. And I am sure that many of you out there, and I've even seen in some of the comments already, that I missed your favorite misconception. So you can put those in the comments as well. And with that, I am going to invite Stacy on board here, and her cat.
And Rocky.
And a big tail.
He has a lot to
I hope
say.
that he's not showing me the side of him, that what he thought of my talk there.
No, he just came in. Well, that was very good. And you ended on the right note, because that's what my mom said to me on the phone yesterday. It's like, we should just plant trees. As she's sitting in Pennsylvania with her, what was it, 95 at 5 o'clock at night? It's
oh yeah,
it
was pretty hot here in New York, I must say. Pretty crazy.
Yeah, and yeah, I kicked it off by it's like, Mom, they had to cancel the parade in Philadelphia, of all cities, to cancel the 4th of July, mega celebration. That's one you would think would still go on, but that's how bad it is. My gosh,
okay,
you're so funny. The one thing I wanted to mention, because I have a particular about CAF standards, which Obama implemented. You had mentioned, I think you had kind of said, well, people got more SUVs because fuel was cheaper and blah blah blah, whatever. Well, actually, or
and taxes
they were made
too
more efficient. Yeah. Actually, it's a whole the auto manufacturers got a
tax break
pass. They got a pass on anything that is using a truck chassis.
Correct.
So they started making things that were more like cars on truck chassis, and those are SUVs.
And it's worse than that, because not only was that true, and they got a pass on the fuel standards, but they also got a tax break if the car weighed more than a certain amount, 8,000 pounds. I don't remember the exact number. Then, if you bought it commercially, for business, you got a tax deduction on that car. So all these Escalades and everything like that, they met that weight number. So the worse you made your car, the bigger your tax break. So it was a number of things that conspired. But the whole idea, theoretically, was to make cars more fuel efficient. And what happened? You can't buy like a normal sedan car anymore.
It's what eliminated.
Car and it didn't. The bottom line, it didn't do anything.
In the United States.
The bottom line, it didn't lower emissions at all. And at the best, you would argue, well, it actually lowered emissions compared to some counterfactual that didn't occur. That what if we hadn't done that? But even then, I think it's pretty clear. Again, it's Jevons paradox. You make something more efficient, it uses more energy in total. Your car might use less, but there are more cars driving longer, and more people flying to Spain. Especially when you expand, if you put the box right around one car, then it does save energy. You put the box around all cars, and then you kind of see, wait a second, it's not. When you put it over the system, the human system, then you realize it didn't save energy at all, because whatever savings came from that car was put into some other fossil fuel burning emissions thing, like flying to Spain or investing more in fossil fuels. And so it's very clear that it didn't work.
And RJM just asked, is the SUV tax break still in place? And it's yes, that it's not for just any SUV. It's for if you're using it for commercial use. So any vehicle that's over the certain weight, but you are have it registered, commercial plates, etc. That's right.
Yeah, and I'm not even 100% sure what the latest is on that, but I know that certainly was true in the
Well,
past.
and I
But
know
it still
even
could be.
in Biden's administration, they had it that, or, and actually, I can't even say if it was, I know it was in the proposed wording, and I would assume it passed. It was that if it's a larger vehicle, or a higher price tag vehicle, you got more in your tax credits. Like if it was an electric vehicle. So yes, electric vehicles are heavier, even if you have a sedan. But this was more. This was dollar amount. So you go buy a spendy truck or SUV or whatever that's electric, you got more of a tax break than if you bought, like a normal sized car.
Yeah.
And of course, there were no subsidies for electric bikes, which is what
So
I would prefer more people to be riding.
so let's see.
Um,
I see one here about SRM and energy. I pop one up here.
yep.
Okay, so from who's this from? Yes, well, from Brittany. Okay, CCS will cost a lot of energy as well as SRM, though, or am I wrong? Well, let's first do the last part first. SRM does not take a lot of energy at all. Doesn't even take a lot of money. Estimated to be maybe $10 billion a year, maybe just 200 airplanes flying to put the sulfur up in the stratosphere. You say, well, 200 planes? That sounds like a lot. There are 100,000 commercial flights every single day. 100,000 commercial flights every single day. So this would be, point nothing on it, and the amount of energy is actually very small. I mean, it's almost nothing compared to the energy it reflects out into space, and therefore cools the Earth. It cools the Earth by many Hiroshima atomic bombs per day. Hundreds of thousands of those. So there's no comparison whatsoever. The same is true in CCS in a different way. It actually does take a lot of energy. It might take for a cement plant maybe 20% of the energy of the cement plant to run the carbon capture. Now, the good news is you'll capture the carbon from the carbon capture plant as well. And so it will make the cement plant low carbon emitting. And that's a very hard thing to do on a cement plant, by the way. You can spend a lot of time on that one. But the thing is, while it does take more energy, releasing a cement plant releases 1.5 million tons of CO2 a year, which is an incredible amount of CO2 from a single plant. And you put that up in the sky, and the amount of energy, the heat that's going to trap over thousands of years is just mind boggling. It's crazy. I mean, talk about that in terms of Hiroshima atomic bomb. You wouldn't believe it. So while that does take some energy, it will be relatively clean energy, and people will argue with that. If you use natural gas, you might have fugitive emissions, but you don't have to use natural gas. You can use geothermal energy, and when you won't have any carbon emissions. So there's a lot of things going on there. But the bottom line is SRM doesn't use energy, hardly any energy at all, and CCS uses some reasonable amount of energy, but the amount of energy it stops in the Earth system is many orders of magnitude more. Okay, what else do you have
Oh,
there? Oh wait, we
yes.
also have I
Yeah.
think
Why
we
don't you bring
have
in
Eli
Eli?
here. Let's go to Eli. Hey Eli, welcome.
Hey, thanks. So I've got a few extra myths. Forgive me if you included these. I had to join late. One is it's a climate scam that we can point to people who are talking about climate, and we can see that they're going to make some kind of money if we do what they're recommending. Well, I think the scam has been cornered for a very, very long time by the fossil fuel industry, which has, literally and verifiably been spending huge sums to influence both both political systems around the world and public opinion to argue that it doesn't exist, so they can continue to make money. So if you look at the the money on that side of the ledger versus the money that, say, Dan Miller is going to make investing in direct air capture, right?
Yeah.
The influence of the money that's for the status quo is far higher.
Yeah, people think that first of all, I'm not invested in SRM. I did invest in CCS many years ago, before it was a thing, before anyone even heard of it. And because I just realized, well, we don't survive without this, so we better start developing it, even though it didn't really have a good business case back then, because there were no policies around it. There are some policies that kind of support testing of it, or demonstration of it, but not really large scale deployment. And when it comes to SRM, I don't even know how you make money. There is one company in the space that's venture backed called Stardust that raised some money, but it's not clear to me how you make money in this. SRM is something that the government implements. It's a little bit like military operation in a way, and I don't see how that becomes a commercial operation. I mean, Boeing might sell like 200 more airplanes, not a big deal. And the oil and gas industry might sell a lot of their sulfur, which is they're collecting in literal mountains. It's pretty crazy to see. But otherwise, SRM's not a big commercial operation, as far as I can tell.
But even if there were, I think we have to remember that, let's leave aside the question of whether capitalism is good or bad, or socialism is good or bad, or government regulation is good or live in a world where big problems take economic activity to solve, and it's generally believed that if you do something good for society, there should be economic rewards for that. Now, if we
Right.
want to argue that that whole system is bad, that's a different discussion, and it affects a lot more than climate.
Well, those people
So
don't argue against the fossil fuel industry getting huge trillions of dollars in
yeah,
subsidies every year.
yeah,
They don't
yeah.
argue about. They don't seem to be trouble. I don't even understand. I don't understand the concept that they complain that solar and wind makers make money on their solar energy and wind, wind energy. There's something theoretically wrong with that, but fossil fuel energy, that's totally fine.
It's great.
There's no issue there. There's nothing to discuss. It's always very strange how there's a very, I don't know, narrow view of things among some people. But
And
okay.
and so I got a couple of SRM myths.
Okay.
One is that we can avoid SRM.
Right.
If we were going to avoid SRM, we had to make major changes, like in the 90s, most likely, maybe even before that. Certainly by the 2000s, and not embarking on fracking and increasing energy consumption and emissions from there. The reality is, as we've heard on the show, is that there are planners in the Pentagon who have gamed out climate risks, and they figure that at some point, if global warming gets bad enough that it threatens wars and such, they'll embark on SRM. And if they don't do it, certainly someplace like India or Pakistan, which is going to be really badly impacted first, a government like that will either have to embark on SRM, or become a really vicious repressive regime to not deal with it. And I think the incentives there are pretty clear.
I think it's also really important to note, and this is something that this week, especially in New York and Washington and other places, and Europe for that matter, that this is the hottest decade ever. I mean, in human history, since humans have walked the earth. Yeah, longer ago, sure, when there was a whole different set of species and different levels of oxygen in the atmosphere. I mean, yeah, it was a different place. But now it's the hottest decade in human history. And this is the coolest decade forevermore. Period. no matter how much we reduce our emissions, this is the coolest decade forevermore, unless, and there's only one unless we do SRM and CDR at some massive scale. Well, SRM to cool it temporarily, and CDR at a massive scale to bring CO2 levels down. And that's the way it is. So, and again, it's not like 3 degrees is a little worse than 1.5. You know, you hit a point where everything just starts to fall apart, and we're starting to see that in some places already. So, yeah, so we have our choices. So far, we've chosen not to choose anything. That might change, I think, as things get worse, but we do have some tools in our toolbox if we decide to use them.
The point is that our past choice to not do anything constrains our future choices, and the reality that is very likely to play out is not one where we don't do SRM. It's one where we do SRM possibly in a haphazard way.
Right. And by the way, you don't want to, for example, I mean, the thing that seems obvious is that India would just do SRM over India, for example, and that actually doesn't work out well. When you do SRM on a regional basis, it does really disrupt weather patterns nearby, and shifts wind patterns, and all kinds of stuff happen. You have to do it in a controlled manner, starting at the poles, and and do it carefully so you balance, you don't shift whole wind-ish patterns around the world. But so anyway, we can do it.
And that can be true. That can be true at the same time that it's also true that, for, whichever regional actor, they're faced with something that's so bad that they'll just take that chance.
Yeah. But there's a lot of, and we didn't get into all the risks of SRM. Yeah, you can start a war or whatever. You got to remember that, even though I didn't mention it today, we are doing SRM right now on a massive scale. We're putting 70 million tons of sulfur dioxide into the lower atmosphere where we breathe it, and that helps contribute to the deaths of 8 million people a year, 1 in 5 deaths, and you don't hear a word about it. It's it's insane, and we're doing that, and because it is bad for health, we're starting to clean it up, and because it used to be 100 million tons, but now it's 70 million tons. And as we clean it up, the world is warming more rapidly, causing the heat waves and crazy stuff that we see. So it's not like we're not doing it. The only reason that doesn't count as SRM is because we're doing it by accident. And that's the only difference. And of course, doing it, you say, well, what about the health effects of SRM? If you do it correctly in the stratosphere, that's not where we breathe it. And as it falls out mostly as rain, so you don't breathe it. And it falls out mostly over the oceans where you don't breathe it. So overall, doing SRM in the stratosphere, as David Keith estimated, is 1,000 times safer than the way we do it today. And again, the only reason we don't count it is because it's done by accident. And that's why I think that the way to do SRM is that we're going to start an advertising company and putting big, huge Coca-Cola signs in the stratosphere using sulfur. And we're doing it to make money on advertising. And as long as that's our purpose, and it won't matter that it will also cool the earth by accident, then maybe that's the way to take care of all of this. So only slightly in jest.
The other SRM myth is, and this is not what people widely think about, but the people who are aware of it, and I think that includes like the military planners, that once it's done, once we do SRM, well, that'll be it. That will solve the problem. And that was actually Edward Teller's idea when he analyzed this with a couple of other scientists in 1996. But their goal was actually to do massive SRM so that we can keep burning fossil fuels. So the moral hazard argument actually does have a bit of a precedent there.
Although it was done actually first proposed in the 1960s, I think, to President Johnson. There's something that we might have to do.
Yes.
So that was a long time ago. Stacey, any more?
A couple things here. So at 10:50, I don't know if you still have access to it.
I can see it. Yeah.
Jean said, "What do you think or why do you think that the agriculture system is never or rarely brought up to be discussed as something with a big impact in the climate? Is it an untouchable topic?
Well, I think it is brought up a lot because it is, I mean, so when the IPCC talks about cutting emissions, they realize we're not going to be cutting them from agriculture, which is why they propose 10 gigatons of CDR starting in 2050, so that we don't have to reduce it from agriculture and we can just keep doing agriculture the way it is. I think people think, well, we have to eat. Now, of course, a lot of those emissions come from cows, and cows are a very inefficient way to generate calories. I forget what the numbers are, but it's, the amount of food input for a calorie on a cow is like tiny compared to growing crops, and even chicken and pigs and things like that are much more efficient. So yeah, so it's true. There's a lot of work, however, I would say, in making agriculture more efficient in the climate space, making I was looking at a company earlier last week where they help improve photosynthesis on plants by spraying something on them. There's others that try to generate fertilizer right in the soil next to the plant rather than at a factory far away. I mean, there's so much work going to make agriculture more efficient. You got to remember also that there was the Green Revolution, and there was a thought that, boy, it was going to be a big die off in the human population, and it never happened because of the Green Revolution. Well, that Green Revolution also helped accelerate climate change as well, of course. So it's all tied in. You know, it's a very difficult systems problem. It's a wicked problem, by the way, to deal with climate change because of all these interactive elements.
You know, that reminds me of a question I had from about last week's show, which, Jean, I can't remember if you were there or not. You should watch it. It's about methane eradication on farms. And it was very interesting. But I feel like you were saying methane something 2/3 of CO2. You meant not, because I've heard you say so many times how much more powerful methane is than CO2, but you're talking about the degradation of methane then becomes, or 2/3 of CO2 is methane, or formerly methane.
So it was the ratio was flipped. It's 1/3 of radiative forcing due to carbon emissions is due to methane, and 2/3 is due to carbon dioxide. Somehow early in the conversation that got flipped.
No, but no, I actually just looked at this last week. I believe it's, as one of our guys said, it's methane is 2/3 the warming of CO2. Now, but you have to be really careful how you say that. It's 2/3. So, by the way, 120 parts per million of CO2 causes X amount of warming. 1.2 parts per million of methane causes 2/3 that amount of warming. That's why methane is 120 times as powerful on a pound for pound or ton for ton basis as CO2 is. But because there's also cooling from aerosols, it's not, you have to be really careful what you're comparing to. but methane causes around 2/3 the warming that CO2 does. But if you added those two up, it would be way more than 1.5 degrees. So, but we're at 1.5 degrees. Now you cut it back from the aerosols, and that's where you can get in trouble looking at 1/3, 2/3, and things like that.
Yeah,
So I didn't make it any clearer, did I? But
the way to do that, the way to do that is to look at the radiative forcing, how it's grown. There's a page on Wikipedia on radiative forcing that has
and in IPCC
really shows this. Yeah,
or the IPCC it shows 2/3 compared to CO2.
Yeah,
like
well,
CO2, methane.
Yeah, but so you have 2/3 total radiative forcing, and either say that one unit of that is due to carbon dioxide, then another 0.5 or 0.6 units of that is due to methane. I think that clarifies it.
Maybe. Well, I don't think we did a good job here, but that's okay. Let's keep going. Let's do a couple more.
Okay. Well, one thing that was in the chat about, what about solar farms? which my mom mentioned there's one, back in nowhere, Pennsylvania, like a huge solar farm. And I'm like, oh my gosh, please send me the information about it. I want to know. I mean, she's having, raising her eyebrow at this. And I'm like, it's wonderful. She's like, why isn't my energy bill going down? And I'm like, it's not.
Oh yeah,
your
well, so
solar farm.
California, we have a lot of renewable energy as part of the grid, and we have like the highest price of, well, one of the highest prices. The reason we have one of the highest prices for energy in the country is not because we're using renewables, but PG&E has to pay billions and billions of dollars for burning down Paradise, California, and also now has to spend billions and billions of dollars to do tree trimming, including right around my house. They come by all the time, and they're looking at any tree branch that's coming near a power pole or power line, and they cut it. And they're really good at it now. They didn't used to do that, and they're doing it like a couple times a year and all over the state. And it's very expensive. Plus, the liability for the damage they've already caused is so huge that they've raised energy prices tremendously. So climate change is leading to higher energy prices, but it's not the renewable side. In fact, you could, put your own renewables on your house with a battery and you don't pay them anything, and you have free energy for 20, 30 years. So yeah, you got to look at where the costs really are. It's not it's not the supply of the actual energy that's causing the high prices.
Well, so I think that some people were, just like you were saying about Jevons paradox, that if you make something, I mean, it's not cheaper in our case in California because of the reasons you just mentioned, but if you're making, with batteries or wind supplement or whatever, you're making round the clock renewable energy that hopefully should reduce prices. Will people use more? Is it a good use of the land, etc.? I mean,
well, you can control it with policy. If by the way, I mean, renewables are cheap and they're scaling very large. All of that energy, all renewable energy so far has gone to new energy supply. None of it has reduced fossil fuel energy yet, because we know that because fossil fuel energy is at a record high. So it's not possible to reduce something that's at a record high. But you can do it more carefully if you have policies that control for this. But if we don't do that, it's just going to get cheaper and we'll just use more energy. It's true. I mean, it's true. So Jevons paradox is true for solar as well as for the steam engine. I mean, it still applies. And by the way, the other thing we didn't mention for very high energy costs around the country, and that's data centers, that they're trying to take all the energy they can, and that, and that's supply demand. So they have very high demand, and there was a limited supply from the grid, and they take it and they raise your prices. So you're paying for that AI through higher prices, certainly in California and other places. So there's a lot of factors. It's not one thing. You got to look at the whole thing of what's, it's liability, it's tree trimming, it's AI, it's, regulatory, this and that, and whatever.
Yeah. Dan, can you pop up what Jean just typed at 11:23?
Let's see. Jean at 11:23.
That's the thing we really need.
Okay, it says in Costa Rica, the electricity is owned by the people. No one makes a profit, and 99% is renewable. Well, that's great. And we do that also here. So in California, in Alameda, California, where we put a plug in here, the Pacific Pinball Museum is located, and I help fix pinball machines there on Monday night, so you can play on Tuesday through Sunday. It's a great place, pacificpinball.org, located in Alameda, California, which is a small town right next to Oakland, California. It's right on the water, it's a little island, and it has its own municipal energy provider that's all renewable, or it's all low carbon. I don't exactly know what all the parts are. It might be some water stuff in there. And the prices are cheaper than we pay next door, right? And also Marin County in California has their own municipal supplier. All those things, they have lower prices. Now, so San Francisco wants to buy the telephone, the power lines from PG&E so they can do the same thing, but PG&E wants to charge them a lot of money, and that whole thing is going on right now. Yeah, this is all political and it's lobbying and paying off politicians because the power providers make a lot of money, right? That big difference in price between San Francisco and Marin, where's that money going? Well, it's going to pay the lobbyists and the corporate interests. So I agree. There are definitely better ways to have municipally owned power providers would be a great
Well,
idea.
and LADWP is a huge municipally owned utility, so huge that historically it has affected things in California in an outsized sort of way. We have the aqueduct that we have due to its forerunners. But we the privately owned utilities, SoCal Edison.
Yeah.
So
Okay,
good.
Anything else here? You want to finish up your next
the
few
other
minutes?
thing that was it caught me. RJM Hudson's Champagne said, "What are the best arguments against degrowthers?" And then someone and I was like, "Oh, okay,
what?
that's a question." Against degrowthers, and then
degrowthers.
Someone popped in after that. Wait a minute, why do we want to argue against degrowthers? Yes, I don't.
Well, you want to see the arguments against degrowthers? Watch our recent interview with Adam Dorr. But we also have another one coming up. I don't know. It's not exactly on the schedule just yet, but pretty soon we're going to have somebody else take the other side of that. So we'll degrowth and is an interesting topic that we'll continue to go into. Okay. Great. Okay. Yeah. Well.
So I did want to finish the other myth on social management. That once we figure it out and we do it, that's going to be the solution. If you avoid massive extinctions in the ocean, because it doesn't do anything about the fact the ocean has been a quarter to a third of the carbon dioxide that we've been emitting, and as it does that, some of that becomes acidity, and that threatens marine life, whether it's things with shells or phytoplankton, and that's a massive ecological disaster which people don't understand. It will affect anybody whose diet depends on seafood, because the ecology is interrelated to how much food the ocean produces for us, and it also affects in the future how much CO2 the ocean can continue to take up, because as it gets more acid, it takes up less and less, so more and more stays in the atmosphere. So SRM is not a way to dodge reducing emissions, and if we would like to make our planet better rather than just stop making it worse, it's not a way of avoid doing carbon dioxide removal, whether it's DAC or other forms.
Yeah, so with that, I want to remind everybody to please like and subscribe. Also, leave a comment and let me know what of these 10 things, which did you like the most, which did you like the least? And then, of course, which ones did I miss altogether? Maybe we'll do a whole other show on misconceptions that were left off of this version of the show. And thanks, everyone, for joining us. And we have some interesting guests coming up soon, and we'll tell you more about those in a little bit. And Stacy and Eli, thank you so much for joining today.
Good to see you, Dan.
And everyone stay cool out there if you can. And, I have to say, I'll just end with this, is that when I first got involved in climate change in the 1990s, when I first learned about it, and I go, wow, this is something, I had this vision that when I got to my age I am today, that we would first see the first inkling of something that you could attribute to climate change. Yeah, it wouldn't be obvious to everyone, but if you really knew where to look, you'd be able to see that climate change was actually happening. It shocks me that it has become so obvious so quickly and to such an extreme level. Mm-hmm. It's really amazing how fast the Earth can change when we push it too hard. So we got a lot we could do about it. We're not doing much, but we can try to figure out how to make that all happen. So with that, thanks everyone for joining us, and we will see you next time. Bye-bye.
Bye.
Thanks, everyone, and bye.